Okay, so today we're going to talk about applied examples of biomorphic design. Okay, and what does that mean? It's a difference from the conventional sort of robotic design in that it wants to basically make things that are simple enough to be mass manufactured here in Hong Kong by the millions at a price that customers are going to want to afford. Basically, who the hell am I? Well, I was a robotics engineer, been building things all my entire life. I basically was a university professor for a good number of years. I was also a mad scientist at Los Alamos National Labs in the United States, where I was building tons and tons of things to basically explore Mars and moons and look for unexploded mines. And for the past 13 years, I've been basically here, turned from academic into industrialist. That is, what does it take to basically take something that you know enough about so that you can put it on the shelf? And this has been one of the interesting measures that if you're a robot builder, I have to basically say you always go through these three stages. Number one, robots to impress yourself. Number two, robots to impress your supervisor. And level three is robots to impress your customers. And that's really interesting. What does your robot do right now that can impress someone when you're no longer around to press the buttons? And that's a very important distinction, because when you basically know that, that's when you can come to Hong Kong and start mass manufacturing this little guy right here, which has just sold his 12 millionth unit at $80 American. In 2004, our first one sold for $80. Today, you can go down to the local Toys R Us and buy them for $80. There's more functions in it than Darth Vader's underwear, and today I'm going to talk about why and how it winds up basically being pretty much dominating the world in terms of humanoid robotic sales. So, what is wrong with real robots? You'll hear an awful lot of other people in this workshop basically talking about this. Robotics are futuristic fun, but the fact is they're complex, they're expensive. Conventional sort of set point design basically require a duty and a dedication and an expense that requires usually very deep funding pockets. The thing was is that about 14 years ago I asked, this fundamental question, if it's the future, where's my robot? It's one of the last unfulfilled promises of the 21st century, right? You can't do anything about flying cars or personal jetpacks, but one of the things that I knew that I could do is basically fill the world with my little plastic robot buddies. So I came up with sort of like a brand new level of what I call the reductionist philosophy, and you can find tons of websites and all kinds of other things that basically talk about this. Complexity is interesting, but how to make robotics better? Well, reduce costs, reduce complexity, increase exposure, right? In other words, get the cost of the fantastic components down to something that basically is affordable, mass manufacturable here in Hong Kong. Reduce the complexity so that factories can put it out and do things, and then put it into an extremely attractive package that small children and girlfriends will basically allow you to buy. Okay, and that's basically an important measure. One of the questions I asked about the world of robotics is, could there be minimal elegant solutions? Because why make something simple and elegant when you make it complex and wonderful, right? And that's great because you've got a long time to fill before you get your PhD. But the cool thing is that if you're going to mass manufacture something, it has to be reduced down to the smallest possible components. And the big question that I also had was, how long would it take? If I was to evolve robots from a lesser state to a higher state, how long would it take for me, basically as a human being, to force the market evolution on my little plastic friends? Well, two disciplines were created. Biomorphics, a methodology of evolving robot bodies from lesser to greater competence. And the advantage of being able to build minimally is that you can build something and see whether or not it lives or dies or fails in the real world, and then immediately put it aside and then start working on a brand new one. And you evolve robots in this particular way. And I started out basically doing all kinds of different things. And that I basically said also beam robotics, the educational effort to make the technology accessible. And if you go online, there are just millions of websites, not mine. I mean, they're all done by hobbyists and various other people who suddenly took a handful of transistors and suddenly realized, wow, that was fast. And that's really important because maintaining an interest in a project, especially a robotics project, which winds up facing what I call computational complexity. And that is that for a linear increase in effort, an exponential increase in cost and effort is required for most robotics projects. The nice thing about these things is that you build, it satisfies, you move on, and the fact is that it basically moves at the level of your particular research interest. Biomorphic is 25 years old now. Oh my God, 25 years since I basically took apart all kinds of dead laser printer cartridges at the university and tried to build like the first robot floor cleaner that unfortunately wound up getting the crap beaten out of it by my cat. Because what I found out, the thing was self-contained solar power. These solar cells would charge supercaps and then it would start to move, and it would basically pull a small brush around. The idea was a machine that would essentially clean floors. And what I did is I basically set it up, basically it was very small. The cat attacked it, so I said, no problem, I'll just change the parameters. And what did I find out? A cat will gladly wait 20 minutes for your robot to move again before killing it. So, these are the sort of things that you just don't get inside computer simulations. Although the robot itself could be simulated inside a computer, simulating my feline at that time was basically a bit of a conundrum. The circuit is amazingly simple. Integrating via a neuron. What happens is that this simple little Schmidt-like trigger mechanism uses the motor as an inductive kick. So essentially it's a modification of a Colt's oscillator. But the nice thing is that you can build this thing entirely out of a dead radio and a dead calculator. So the whole thing was trying to come up with something that you could basically put out there. And the main thing is that if you've got a pile of junk in your junk drawer, chances are you've got all the parts that you need to basically build this thing. The actual nature of the behavior, we did tons and tons of studies on it. I mean, the nature of the Schmidt-based integrating fire basically is that as any signal comes in, and then when you basically get to relaxation, that's when you want to get a transition the way out. What that means is that the actual tau, that is the time it takes for this thing to open and close, is directly proportionate and independent at this actual neuron. What does that mean? Well, it means that when you take large numbers of these things, either as integrators or differentiators, and put them into a beautiful little circuit like this, what's interesting is that you'll notice is that the outputs, which go to the motor, directly feed back to the inputs right here. Well, what does that look like? This is probably one of the most useful circuits I've ever come up with in robotics. Because those of you who might have played with servos know that if it's a big servo, it's going to cut off your finger, and if it's a small servo, it's going to cause all kinds of problems. This little circuit right here, which is exactly that circuit, is just 6 transistors. It takes a feedback from the motor itself. So why do you need servos when the motor itself is a measure? So anybody who's ever wondered what it's like to hold on to the end of a 5-watt servo without having to get your fingers ripped off, right? I'm going to come up and play with this thing. The neat thing about this circuit is that you then expand this oscillator. That is not just one neuron, but multiple neurons. And the fact is that you want getting these wonderful little emergent properties, these emergent patterns. And this was becoming very, very convenient in coincidence, although we wanted to basically sort of have our ass handed to us by a bunch of biologists who say that, oh, there's no way that could possibly ever be appropriate. But the fact is that in terms of performance to silicon, and that's one of the big things that you need if you're going to basically try and put something on the shelves in Hong Kong. And that is that how many different sort of features can you get for the smallest number of transistors? Because that directly translates to cost. And the neat thing is that when you expand these oscillators quickly, after 8 neurons, you want to getting an exponential number of patterns. So all these little two-area necklace functions, which basically mimic all the characteristics of walking things, and it's very convenient. So you take 2 of these oscillators, and this is a 6-element oscillator, you put it into a machine, you quickly organize it in legs, and next thing you know, you have something which basically modifies itself, responds to stimulus, and then relearns to walk, literally just while you walk. And that's so cool. I mean, just imagine that. I mean, like everybody's ever sort of, seen a good Marvel comic, right? Like, oh yes, I built a robot, and now it's gone evil, oh, what a shock, right? Well, I'm one of the only people in the world where that's actually happened to. Right? Because the neat thing is I don't have to program my robots, I just have to power them on, and then hope to God they don't steal my lab suit and basically run off into the dark. The cool thing is that nervous nets, okay? Differential chains of differentiators, right? Basically coupled with neural nets, which of course are parallel arrays of integrators. They basically remember dynamic rhythms. Just by pure luck, that you can feel that when you actually feel that sort of a thing moving back and forth. And you can certainly see it when you put, like, not just one motor, but say 3 or 4 motors into a simple little mechanism, right? Because first off, you simply realize, what's great about this? Well, it finds resonance, doesn't it? And does it walk efficiently? Yes, it does. And the cool thing is about that is that why is that important? Well, not only is it the smallest number of components, 14-inch high, 7-motor robot, 36-hour battery life, regular batteries. Now, those of you who might actually know anything about conventional sort of servo-based robots in the Asimo style basically recognize that that is approximately 20,000 times more than the usual battery life of such things. And that winds up being something which is fairly important, because if you're going to sell something on Christmas morning, Batteries in Christmas morning better still be working by New Year's afternoon. Okay, otherwise this toy is going back to Toys R Us. So I mean, coming up with the efficiency, the necessary efficiency. The nice thing about the circuit is it automatically finds the dynamic rhythms necessary for stable walking patterns. Integrated neural network arrays remember static patterns, and that is that you can actually give these things by coupling them with neural nets. You can want to give these things like the ability to remember previous patterns and the conditions by which they can swap back and forth between the two, combining two form devices with significant practical competence. And the cool thing about that is that you can set these things up, and I gladly invite us to play with these things and have them wander around. The remote controls here, or just press the buttons and they'll start walking. And you sort of realize that the real beauty of these sort of things is the ability to be able to handle walking over cables, wires, or otherwise. They don't require the pristine sort of world that normally we have to put in for, like set-point servo-based designs. The thing is that I built huge arrays of these things to see what the nature of the nervous properties are. I coupled my devices with lots and lots of blinking lights for no apparent reason, because I had this dream that somehow I'd be able to pattern match the lights to the actual function. But no, what's funny is that when you actually see these things walk, when you set up the actual architectures, and then what you do is you basically look at the state space, translate it, and so for example, here's a neural network brain based upon a beautiful symmetric structure. These down here are the motors, and then you want to build yourself a really beautiful cockroach. What's fascinating is that I hate bugs, but I'm very good at building them. I've built hundreds and thousands of them over the years. And the thing is that this basically shows what happens when you have a neural network hooked up to a nervous net. You power it on, it has absolutely no concept of what it is or where it is. In seconds. Okay? Now just imagine how much that impresses your supervisor. Basically say when you say, yeah, of course I programmed it. No, you didn't. But the fact is that it sorted itself out, but you're the one that gets the PhD. Bonus. So the whole trick is to try and come up with mechanisms that, in a very biologic sort of way, go from a zero state to a knowledgeable state about being able to walk through the world. Biomorphic beam robotics has generated thousands of roboforms. We're all around 15 species. And the cool thing is that as a compulsive robot builder, yes, I'm that sort of dweeb. Basically, it doesn't stop me from starting to build hundreds of these things. You can see websites, it took about 25 years to basically build these things. And the nice thing is that each one of these things are different types. I mean, everything from rubbers to micromice to complete robot walking chess sets to self-contained solar-powered floor cleaners to tally-ho automatic bedwetters, which are robots that leap on your ex-girlfriend's bed in the middle of the night and pistols on her. I mean, these are the sort of things that essentially I can build, right, as a standard part of my actual mandate, which, of course, is to fill the world with my evil robots. Just in case you're interested, kits and various plans are available through Robotics, basically out of Canada. We've been selling these kits now for years. So the thing is that there's just an awful lot of advantages to this particular sort of minimality, fast, prolific, inexpensive, disposable, accessible, open source. And what I found came to Hong Kong, affordable. And that turned out to be something which is very important because it's also manufacturable. And the thing is that, as I said, performance to silicon. You don't think you're going to go, oh, geez, I can high quality processor chips that basically have the power of an Atari ST for less than 10 cents. Yeah, fine, you still got to sit down and program the damn thing. And then even the thing is that, say for example, you basically put a project like that aside, and then you have to go back a month later. You ever try basically edit your old code? Even from a month ago, you suddenly realize that the real problem with processors is that they allow, as long as it keeps on working, it's fine. But if you ever have to go in and edit anything, right, it's actually easier to start from scratch. The nice thing about all my technology is that you can see it. The transistors are right there, you can pick it up, you can explore it, and these guys are the same way. They're designed so that when you open them up, everything inside, color-coded, organized, symmetric, structured. So basically reverse engineering these things and modifying them for your own purposes, very, very easy. Scale and variant. I built things 76 feet high, I built things like an inch long. But the thing was that years ago I got this fortune cookie. And I suddenly realized, okay, well, time to go someplace. So I decided to come here. Basically, I crashed my robot on Mars, so I basically said, okay, no problem. Let's see if I can actually mass manufacture these things. So I took some of the very first insects that I basically had manufactured, and we wanted to put them into these things. The biobugs were really big in 2001. The nice thing is that the mechanisms themselves were great because they had a super long battery life, regular batteries, and we took them out to White Sands, New Mexico, and basically just had our own little robot swarm, where of course I was the king. The nice thing is, as I said, is I suddenly realized the great thing about robotics is what does it take to have fun enough with it so that you can in fact be a James Bond villain, and I'm just one step to the left. The cool thing is that, you know, like how do you basically build the Robosapien? Well, the cool thing is especially in this town, I mean, like go up to Mongkok and take a look at some of the design shops. You walk in and you sort of realize there is a dedication, there is a religious conviction to the beauty and the future and the power of having your own giant robot here that essentially is everywhere. The movies, the TVs, right? So what would it take to make something that actually works? Well, again, I've looked at sort of like, you know, some of the beautiful Japanese designs. Mechanically, these are wonderful, but battery life and expense and a variety of other things basically are absolute killer. And the other thing that basically, even now, you go up to Mongkok and you see these things basically for an awful lot of high quality things, and look at that. You know, that is just too damn much for a servo that can still either cut your finger off or basically destroy its gears based upon what you're doing. The cool thing is that all these systems are based upon my own open motor servos, which are less than 27 cents each. And why do they cost? Because when you make 27 million a year of something, you get cost reductions. Okay, and that turns out to be something pretty cool. These things are now an industry staple. And one of the reasons that I came to Hong Kong was not just to build robots, but to build the parts for robots, to build the sensors, to build the mechanisms so that other people could see them and then start using them. And the thing is that these have to be very different from cell phone technologies. Half the cost of a cell phone just goes into the licenses for the components in a cell phone. But the toy industry can't possibly work on that. So all these things have to be open source, public domain, extremely made with 19th century technologies. And it's true, I mean, like, it's like some sort of character from a bad science fiction movie. The fact is that when I came here after working for NASA, I simply had to go into China and pretend that I was building in 1990, right? And like some sort of strange science fiction time travel. The first Robosapien was built at the Tilden and Gino Yu workshop in 2001. You can see again, you know, like the little motors that I basically built during my BioBug days. There's the 3 little motors hooked up with an appropriate oscillator structure. The final robot itself, right, 7 motors, actually 8 including one for the neck. The actual controller was 24 transistors. Everybody say, because the thing is that that's all it needed to build a fully autonomous robot system that essentially was capable of negotiating and walking. The other thing I did is I put in what I call KX² suspension. That is that servos and sensors cost. Servos cost something, but sensors cost even more, especially because they wear out over a certain amount of time. And those who've actually seen what happens when an encoder breaks on a high-quality servo and anvils, you know, like basically destroying wires and gears, is something pretty horrible. You see the spring system here? It's very similar to the spring system here. And I invite you to come up afterwards and basically, you know, like, have a feel. What it's like when something basically is like fighting against itself, and the motor itself is its own sensor. The cool thing was that, again, you take 3 of these things, couple together. Those are the very first steps of the very first Robosapien. And the cool thing was that we then just said, okay, well, no problem, let's just get it here into Hong Kong. And what I found was amazing was that when you come to Hong Kong with your prototype, you have to present it to a factory, and the factory is going to put it to their engineers, who basically will then try to recreate their own version of it. Well, if you look at this thing, it's got the largest digital brains. And so, like some sort of funny Frankenstein, what's really amazing is that they put all this digital technology in, and they didn't quite get it right. So, it took us a while, but the fact is that ultimately we got it working. And this is probably one of the most proudest moments I ever had. 504 girls over 1 acre building 2 robots every single minute. And this is something which, again, you know, it's so much fun. I slept on the floor with the girls. I basically only ate the same rice they did every single day. I tried to avoid smoking, but the fact was that it was just amazing to suddenly realize that you were not building one of something, you were building lots of something. And that's astonishing because at the appropriate price, all of a sudden it winds up filling the world. The charm that the robot has, it doesn't speak any English. And in fact, those are its main forms of communication, burping and farting. It turns out that you don't have to have something that speaks in any language that basically is recognizable, but these appropriate things, that is body cons, actions coupled with an appropriate recognizable command, wind up being universal. The cool thing is that one remote control works them all. The thing is that the mechanism itself, again, I basically emphasize, is that one screwdriver takes the mechanism apart, it can be put together, it can be reassembled, it can be modified. You see people carrying all kinds of wonderful things, and these things over the past 10 years, well, just type Robosapien into YouTube and then be said. Which means if you're going to sell something commercially, that is also going to be a major consideration. How do you come up with motors? or you can beat the crap out of it. Now, mind you, I have actually gotten some amazing robots in the mail that have been eaten by dogs, run over by trucks, destroyed by a hurricane. You know, like I lived at the bottom of a pool for 6 weeks. You know, why isn't it working? You know, that's fine. Because the thing is that it's what's most fascinating is finding out that you can have all the fun of building a robot, but try and figure out what people actually do with it. And that's one of the more interesting things that that basically you get when you start interacting with people in the real world. We also built giant ones. Avenue of Stars, for example, we had this thing walking up and down Hong Kong. And you know what the biggest market was? What we found out is that all you had to do was just basically build a giant 2-meter-tall humanoid robot and just have a slot right here that has a $20 input. And what happens, it'll stand still and hold up its fingers like this while you take a picture of it with your girlfriend, right? And we sort of realized that would be the ultimate market for one of these things. You know, like crowd control be damned. The real problem is it was too big to actually go through any walls. It's currently sitting in the basement somewhere, basically hoping you put it together someday. We also work on a variety of other phenotypes and genotypes. So, for example, the Robopet was the idea of coming up with a robot dog, very similar to the Asimo that the Japanese have come up with from a long time. I know that, so I will. And what's neat is that if those of you who lived in Hong Kong, you basically realize that the second currency in this town is umbrellas. And that's exactly what I built this entire dog with. Just a whole bunch of broken umbrellas. It's a fantastic source of extremely pliable little mechanisms that can be soldered together. And it's actually quite believable, and that's what we had to do. 5 motors. What's fascinating is that we're doing something which, again, open loop was able to get itself up, get itself around. The sequences basically showing you how to walk, move, bark, again, you know, like burp, fart, all necessary things that essentially seem to entertain children. And we wound up selling them there quite a few million. Dinosaurs. The cool thing is that in the toy industry, you'll suddenly realize 2 rather interesting extremes. Dinosaurs are infinitely popular because they're so far in the past and never own one. Robots are so interesting because they're so far in the future and never own one. So what we do, we combine the 2 together based upon a paper that I wrote years ago. And the nice thing is that when you start dealing with mechanisms that wind up rocking around resonance, you're no longer forcing a power issue. And that means that you could build a machine that was over a meter long that could, in fact, basically exhibit very believable sort of behaviors. We've sold over 7 million, and we've had to actually calm it down because in a lot of cases it wanted to basically be too frightening for a lot of children. And here's, for example, interesting. This thing is 1 meter long and it runs on regular AA batteries. And it's because it falls into these resonance patterns that it can actually walk in pretty much any sort of surface. What was really fun, one of my fondest memories was the first time you actually get like your first 1,000 of these things we ship out, usually someplace special like Dubai and otherwise, is you have to actually go up to the factory and you're in a room like this, and there's like 1,000 of these things on the floor, and you got a remote control, okay? And I wish I'd taken video of it because you press forward and all of a sudden you get 1,000 dinosaurs that will roar at you and start walking towards you. You just sort of realize, well, there's a Jurassic Park here somewhere. But the neat thing is that you might have a lot of time and put a lot of attention into building one robot. But what happens when all of a sudden you've got 1,000, you've got to get rid of the damn things? Well, I mean, like, talk to me later because I've got, a warehouse is full of those things. The neat thing is finding out, again, not just basically how good the robot is for itself, but how good it is for the customers. One of the great things that I did when I went on my worldwide tours of these robots is that usually it's like, oh, NASA scientists will now speak to the children who basically all brought inside here. So I said, no, look at that. I just powered on the robots and had them walk into the kids. And we knew the toy was going to be a success by the number of fights that broke out amongst these children, right? That was basically a big bonus. Because you got to remember, the nice thing about making something this tough, this reliable, this robust, is that it's strong enough for your kids, okay? Or maybe your grad students, so it depends on how much you're there. The cool thing is that we've had lots of cool things happen with them. TV, newspapers. This basically was the X-Men 3 movie where we were sitting there in the audience with my designers and we saw that and we were just saying, hey, we are a toy preferred by mutants around the world. Of course, my goal was really fun. It's basically like all the Playboy and Playgirl things, and all of a sudden we realized that people were sexualizing their robots. So how to make your robot your own personal boyfriend is something basically might be pretty common. The next thing was that we wanted to just come with a larger platform. That is, this is selling very well. What is the upper bound on what people would actually pay for? Well, we wanted paying for the RS2. The RS2 basically was supposed to be a 13-motor mechanism, right? It's massive compared to the Robosapien. full-size hands, extremely flexible, could sit, get down, get up, at a variety of different sort of things. You see the final sort of design here. But again, the big condition, it had to be inexpensive, completely plastic, and run off of regular batteries. Nothing certainly kind of rechargeable otherwise, because you can't ship them. The nice thing is that I wanted to be using a very sophisticated little infrared sensor tracking mechanism. So the actual emission mechanism is all around its head, and it winds up using a camera in the forehead, which allows it to be able to actually see colors and basically move itself around. Again, resonance. The mechanism is basically over 5 kilograms with the batteries in, but it was able to run for well over 9 hours off of regular batteries. The thing is, in terms of flexibility. Ooh, don't try this at home. So 13 motors, I mean, what is the minimum spanning space that allows you to build an active and functional humanoid? And we sold over 2.5 million of these things. But what was fascinating about this is that we had 1,400 components. It was, in fact, probably one of the most complicated builds we've ever had. We had one entire factory, 6 acres, over 3,000 Chinese girls basically putting together the parts for the Robosapien. And what was amazing is that this was a throwaway pile. This is the sad thing. Each one of these robots had one minor defect in them that they wouldn't be able to sell, and so they were all destroyed. So, just imagine the fact that I had over 150,000 of humanoids that unfortunately had to die just because they could not satisfy the necessary mechanism. I mean, just the waste is just astonishing. But I was glad to find out later on that they're all shipped off to Russia and basically sold as educational toys. But the cool thing is that all of a sudden you wind up getting something which is like, this is reality, and this is hyperbole, and they're pretty much interchangeable. Cool thing was that it wanted to attract an awful lot of attention to significant stars. And then we went on to something which I wanted to work on for a long time, because one of the cool things about working when you, KX-squared suspension, when you basically apply it to resonance structures, you want getting things that are capable of not just moving, in a static sort of way, but in a very dynamic sort of way. So this thing is using only 3 motors, 1 to control the tail for balance, and then 2 for the legs. But it doesn't fall over onto its side, even though it runs on regular batteries. So that was the first prototype I built. Then what we did is we put this beautiful little shell around it, gave it the ability to be able to run, not just forward, but also on its back legs. And it is still the fastest commercial robot toy that you can actually buy out there. I mean, I'm really pleased to see that the industry is now filled with all kinds of fast-running bipeds and various other things. But the fact is that that's something which essentially did very well internationally. And again, it's not just performance to silicon, it's also performance to mechanics. Because whenever you can reduce the mechanics on something, you basically reduce its cost, which enhances its saleability. Performance, basically one of the things that I basically put out, and I try to emphasize again, if you are a robot builder, please put your face next to your robot, okay? Because there's nothing worse than basically like seeing your robot in IEEE journal and it's just your hand pointing at something, right? That's not going to impress your mother. So the thing is that a robot is really interesting because it is not your son, it is an extension of your competence. So a picture like this is nothing more than an extended selfie, okay? So what I recommend you, make sure that you put your face next to your machines, especially when you've got tons and tons of kids. They're basically starting to enjoy it. And of course, like as I said, it was amazing how many major nudie magazines basically wanted my robots to use their models. And of course, I had to supervise. RS Media was interesting because although we did, one of the big things that I'm doing with Biomorphic, and I keep on emphasizing the point, is that this is a technology which acts as a cradle for much more complicated mechanisms. So we came up with a complete Linux-based ARM process, 64-bit flash. This device is basically a walking, talking iPod with an LCD display and a 3-speaker sound system. The thing was that it was about $400, and that turned out to be too much, so we only ever sold about 15,000 of the devices. More used it as a static MP3 player, right, which is a real shame because we thought that basically making a robot at the same price as a cell phone, we wanted basically making it still accessible, but it just did not have any real impact. And this is despite the fact that if you ever watch the famous Big Bang Theory, the RS Media is, been a centerpiece of that show now for well over 7 years. Very famous little robot. New generations of things are quite fun. When I built robots for NASA, basically it was all about what's the simplest way to basically explore Mars. Well, based upon robots from years ago, we came up with this little mechanism. It's only 4 motors, basically a certain sort of angle. This was my prototype, okay? Simple, elegant, beautiful. This is my factory's prototype, oh my god. But ultimately we got it down to something which was sophisticated, smooth, and fast. And the cool thing was, again, is like what happens when all of a sudden you get a robot and a puppy. And you can see the rest of that video on YouTube. There are many, many of them out there. And like I said, one of the cool things is coming up with a mechanism which can actually not just entertain you, but also your pets in the house. So the most autonomous robot we have with a vision system that allows it to see over 2 meters away. It also had a variety of artificial intelligence modes that basically mimic its ability for aggressive stance or exploration. Just just press 3 buttons and you want to select one of 27 different modes. And that turned out to be a very interesting little feature that people really liked because it was an embodiment of sort of like AI that could be commercially available. And this is just it, like, hi, I just want myself a humanoid robot, AI now included, write it yourself. That's not something you're going to use to impress your girlfriend. But on the other hand, there are ways of making robots which want to basically be both useful and otherwise. And this is the RoboBullet. Based upon sinuous robot techniques, nice thing about the chain of oscillator structures that I have is that you put them into a long line rather than select a simple 3-dimensional structure. You want to get a uniform distinct. Fast and scary. The cool thing is that I wanted to hook these things up with sort of like an intelligent light. And that is try and make something which would essentially not just entertain you, but also illuminate you. It uses a 1-bit vision sensor that can see over 2 meters away. The cool thing was it's actually able to sort of see and recognize something and pay deliberate attention to it. So the fundamentals of robot attention is short-term memory, okay, plus focus. And in fact, this is capable of both of these things, even though it wasn't able. But as most space inside, I'd always hope that someone would basically modify these things. The guard mode was actually pretty interesting. So you can put this in your bedroom. When your girlfriend comes in, you can find that she's stealing your Halloween candy. The neat thing was, again, it was the best R2-D2 personality, but when they were sold 100K because it didn't look like something people would recognize. Humanoids wound up being a lot more viable and a lot more valuable for people. And the thing was that both these alien-like creatures basically had a limited sale point because they did not have the appropriate branding behind them, no recognizability, so that people would basically get into them directly. So we worked on something a little bit more sophisticated. It had been 5 years since the Robosapien. The Robosapien was still selling well. But I knew that basically I could take the proportions and the efficiency of this mechanism and increase them again. And so we came up with the Pennysapien. The thing is that when you build a female robot, well, the engineering is in your favor, okay? Center of balance, distribution, places for all kinds of motors. But culturally, if you think that you've had a weird idea for a female robot, you're too late. And it's really strange how basically people distort these things to an incredible degree. We were able to reduce her down from the Robosapien from 7 motors down to only 5 moters with basically like an incredible number of degrees of freedom. And what we did is that this was one of the first machines that we actually used, both set-point servo as well as my KX-squared suspension biomorphic structures. The result basically was very interesting, but this time we got very quick, basically going from our first evolution to our final evolution, which was only like 3 months. And the cool thing is that, because of the shape and style, she's actually quite stylish in a lot of ways. We set her up as a little princess, so to actually teach her to walk, what we did is we set her up so that when you held her hand, and that way we can basically adjust the balance as necessary for like something. Her arms are completely functional, and she can actually sort of draw pretty much anything. And then we built a variety of videos. Yeah, she's fast.
Yeah.
And that's why she was banned from YouTube. The cool thing was that, again, I just wanted to show like mechanical evolution. machine is right here. Whereas Robosapien here has between a 25 to 36 hour battery life. Pennysapien uses both set point as well as biomorphic feedback control, 120 hour battery life from a standard set of AA batteries. I mean, that's just something which allows you to do all kinds of stuff. She has all kinds of little hidden secret modes. So, for example, you can set her up so that she winds up doing little poses non-stop. So if you wanted to sort of, have her sit in your living room, this is a hidden secret. Just mount her head level like that, and she'll keep on posing until her batteries die, and that's about half a month's worth of work. The thing is that that's interesting, okay? All of a sudden now, the entertainment, the fun, basically working and moving with the thing, but that thing right now could in fact display and show off your technology for the length of this workshop on one set of batteries. Feature, not a bug. Neat thing about it is, again, culturally we found all kinds of interesting things. Number one, we had to be very careful in how we painted her, because otherwise you suddenly realize, oh my God, she's quite a nice little design. The other thing we found out, and this is very strange, is that we couldn't put on any clothes on her, not even a headband, because then all of a sudden the customers basically would get complaint letters, basically saying, "Hi, why are you selling a naked doll?" And we're saying, "Oh boy." Well, we couldn't sell one with clothes because then it qualifies as a doll, and that basically makes it subject to 5% inherent import tax through most of the European Communion. So I mean, these are all kinds of little business considerations that are necessary. And the real thing is that she was extremely big in Japan, but what I had to do is that I basically had to remove myself as the inventor, and basically you can even go on to YouTube now, and suddenly realize that there's all kinds of pictures of her kissing her Japanese inventor, because that was the only way to basically guarantee she'd be selling very well in Tokyo. Nice thing is that again we've had tons of videos and online mechanisms, and the thing was that she basically led directly to the Jobot, which again used not just a mechanism for like top-notch walking manipulation, but something that I could actually hear, listen, and do something. Robot. Forward. No. Robot. Forward. There you go. Now again, this is just using like the biomorphic mechanism. What we do is we find mechanisms to find simple centroids. Stop. Hey, robot. Kill audience. And he'll do this for hours. The cool thing was that we wanted something that would basically respond to any voice, any language. It's the length and the power of the tone. And he's great fun. What we wanted to do is I wanted to basically build Bender from the TV series Futurama. Those who basically know the series will know just how much fun it is. But the thing is that combined with these three, you wind up getting a beautiful mechanism capable of all this sort of stuff. Again, the evolution of the design. There's a good reason why all my robots want to look an awful lot like me. One of the cool things about it is, for example, it's a beatbox function. And you can basically pick a pattern like that, you can pick up patterns in voice and a variety of other things. The business from these ends wound up being very interesting. I mean, originally back in 2004, we wanted to start many, many millions, and this is basically what a successful product basically winds up looking like. It winds up going a nice little Poisson distribution, slow decay. But the main thing is that although like about 208, but just recently we've been getting a beautiful little resurgence because there's actually a nostalgia craze for an awful lot of robots, and this is now basically being reflected in an awful lot of our initial sales. So the robots are designed to be inherently hackable, modifiable, and expandable. So the nice thing is that if you stick in, that is, you make a product that essentially is sufficient quality, there's a good chance it's basically going to continue selling for a long time. And that's cool, because the proceeds from these robots goes to building my future robots. Thing is that if you have a marketable idea, some tips, 5 steps to self-actualization through toy building. Everybody has their own approach, but complexity rarely scales downwards. And I say that because people come to me with wonderful ideas all the time, and like, oh, pay no attention to that supercomputer behind the curtain, I'm the great and powerful roboticist of Oz. The reason I basically try to emphasize the simple minimal elegant solutions, that it is so much easier to scaffold from something simpler to slightly more complex than the other way around. Your particular skills turn out to be a major measure of how far and how fast something will actually develop. And something else you have to remember, and that is that for your customers, technology is transparent. How it works is the bailiwick of us, right? We want to know the details. But your 3-year-old son, he doesn't care as long as it burps and farts the cat. Okay, and these are the sort of powers that are necessary. Those are your customers. And that's the sort of level of transparent transaction, a transparent ability of something to basically sort of fit into your world. It's quiet, it's efficient, and its batteries last forever. The cool thing is that it's not just impressing your final customers, it's also impressing their parents. And ultimately, you know, people who basically want to get into much more future sort of design. So where are we going in the future in something like this? Well, I can't talk about that because after all, we're working on new generation technologies that will control mankind, but you can't see that. So instead, I'm going to talk about adaptive new breadboard structures that essentially are going to be now made commercially available. And you read about these things on Make magazine. 5-watt built-in intrinsic metal mechanisms that essentially allow for extreme lifetimes on these things. That is, robots that are made entirely out of aluminum with a lifetime of about 10, 20 years. And the cool thing is that once you've got that, once you've got a super efficient robot that can wander your place to the point where you forget about it being there, now all of a sudden it's just a degree of how do you assign it the appropriate work so that essentially you can now be competent for you. And the thing is that this little guy is basically currently walking around right now is that I love building mobile breadboards. Because the great thing is it's great to select. If it's also stuck against the wall, I can put it on a couch, change its brain, pop it back on the floor, and then observe it over a period of days. Because life is long, and the fact is that having continuously running experiments like this turn out to be quite interesting. Again, full details are available in the recent Nate blog. So what are the conclusions? Well, research conclusions. Minimum relevant solutions? Sure. How long did it take to go from very simple little one-motor, 200 integrated neuron mechanisms to a completely autonomous voice recognizing humanoid? 20 years. Number built? 23, 24 million so far. Goes up and down. The cool thing is that I basically answered my own question. If it's the future, where's my robot? The fact is that for the past 10 years, there they are. Available now in your grocery freezer. Hoping the future generations will be a lot more interesting. Thank you very much. Before questions, I basically like to have people come up and basically you can just start playing with the robots and toys. But I have something else for people in the audience. This little circuit, KX squared suspension, that is motor position without the benefit of servos, where the motor itself is its own measure. The circuit is right here, and you can come up and actually feel this thing. But I've actually brought a handful of the chips. And anybody who wants some, there they are. Plus schematic diagrams. So anybody wants to take some home to play with, right? As I said, there's an entire field of work. And I'm not just saying that because it's a $200 million a year industry, right? You know, just in case you might want to study it for your own entertainment. Don't forget a copy of the schematics. And if you don't get a copy of the schematics, they're available online as well. Just type my name in, there's like 2 million websites. Yeah. Okay. This one thing, when I came to Hong Kong, and someone said, okay, I want you to build robots. I've been doing robots for a long time. One of the real problems with being an academic roboticist is that you always have to be extremely serious because you have to make certain that you look good to your supervisor and your funding source and various other things. They don't want to think that you're basically playing around and acting around, right? So the thing is that it came to Hong Kong, though. If you want something that's going to train you a kid, it's got to have natural sort of abilities. It's got to be able to like talk and evolve and do things that essentially are immediately recognizable and natural. So the fact that this thing is its own little functional clown and has more features in it than you'll find in most video games was absolutely vital. And the thing was that it, once you take the seriousness out of high technology, then all of a sudden you find out its international accessibility turns out to be an awful lot more interesting. Yeah, so it's completely stalled out, right? There you go. Now you actually feel the nature of the adaptive nervous network. So the cool thing is that if all of a sudden you build a giant robot like this, where have you actually seen that motion before? It's in exactly the motion that this thing winds up using to use all of its motors and functions. So 3 of these things are all you need to basically replace the walking mechanism that's currently inside this device. Once you get something which runs on resonance, its efficiency goes up by extraordinary degrees. And there's tons of papers on this. So. But that right there is basically something to allow you to sort of like test any robotic mechanism. Can you hook it up to any motor? It doesn't matter what motor you use. As long as it's like, between 3 volts and 12 volt motor. And the neat thing is that again, the motor being its own sensor, right, is something that's so vital. The motor itself is its own sensor. When the actual load gets to be on a certain sort of level, you need a motor that's essentially 25% efficient. Current load basically party price of feedback. If you simulate it, it's just going to sit there like it's done, unless you basically give it a pulse. Because the oscillator itself is by mode because the actual neurons are mutually. So, are there any other questions? What I'll do is I'll set up the table during the break and stuff like that, and people can come up and press the buttons and like play with the motors and everything.
So I have a question.
Sure.
About the nervous net approach that you're using to control the movement of the robots. Mm-hmm. As I understand it, what you're doing with these robots is you sort of have a certain set of movement patterns that you want the robot to have, and then you kind of tune the network to be able to display those movement patterns.
No, it's actually the other way around. You see, one of the things that I basically like about nervous networks is that they automatically find the optimal resonance for any structure that you might mounting them into. So the cool thing is that you can in fact have distorted or mechanically, like disparate robots, put a nervous network system in and it works. But when the device is mechanically optimized, you can now put it in a nervous network and it will give you some form of functional behavior. Now, as I was basically pointing out on my website, one of the cool things on my slides is that they don't just fall into one resonance center pattern. They fall into a series of them based upon the number of neurons that are actually involved. Past 8 neurons, all of a sudden, the number of actual possible process states explodes. Now, what does that mean? Well, let me show you. For this guy right here, what we found is that there were 2 fundamental resonance states. One, forward walking, big step, and then forward walking, fast step. Okay, you can see that these are directly harmonics of each other. The thing is that you can change the direction, all of a sudden it's backwards. And then even if you're doing something like, say, turning around in place, the necessary phase angles are all there, and they basically fall automatically from the nervous network pattern, which is always fighting to minimize energy utilization by the motors, because the motors themselves are in fact the sensors.
So what I was wondering is if you could say something about the possibility of having this kind of nervous net architecture use some kind of reinforcement learning to learn new patterns of behavior.
Well, it does.
Feedback.
Well, no, what's fascinating about these things is often it starts doing something useful. But how to constrain that and bound that is actually the fun. But the thing was is that, hey, what's specifically going on? Well, that basically requires like a sort of analysis that unfortunately I don't have grad students for.
Well, so with the robot, one of these robots display some. It's not going to be able to display some new pattern.
Yeah, damn sure. Oh no, that's exactly right. Once you get past 8 neurons, the phase difference. Don't forget, because each neuron essentially is temporally independent of every other neuron. All right, unless you want coupling it to like inappropriate sort of pairs.
Let me give a simple example of what I'm thinking. So it seems like if you had a staircase that wasn't too steep, mm-hmm. It seems like, and the friction was okay. It seems like one of these robots, in theory, could climb up a staircase.
And the Robosapien, I can demonstrate it here on like this wire or carpet changes or various other things, or have it walk up inclines. I mean, in fact, this is the device automatically falls into like brand new centroid localizations for handling complexity environments.
So even if you'd never put it on a staircase before,
even if you
put it on the staircase, it'll just do its thing and eventually start to go up. But here's the thing with reinforcement learning. If it managed to wiggle around in a way to go up one stair, mm-hmm. then to go up the next stair, will it somehow have an easier time getting up the next stair, or will it have to wiggle around the same way the second time?
No, because what you find out is that between the centroids of pattern localization, right, there are minimum path gradients that allows it to select only those between individual sort of states. Okay, and I can display that with someone like Pennysapien, for example. It's cool. This guy has 6 centroids, but she has 14. It turns out that when you make something like tall and fairly humanoid, it's just amazing. So, like, the range of different sort of things that automatically came out of these structural patterns. And as we found these things, we measured them, we put them into recording sound machines, and that basically is how these things wind up walking. But what's fascinating is when you get the analog mechanisms, you sort of realize that under stress they can do that. But this is why basically I emphasize not just the nervous nets, but also the neural nets. When you take a neural net and adapt it to a nervous net, the neural net remembers patterns, right, which can then reinforce the actual gradient localization. So, for example, oh, I tripped over a step. Don't do it again, right? Proper binding in architectures of neural nets versus nervous nets basically creates a forced feedback where basically now thoughts are turned directly into actions that can in fact basically sort of like, optimize the device for minimum effort. And as long as this is the most important thing, because a lot of things you're like, well, why is a neural net neural? Okay. And one of the things I suddenly realized is that these things are designed around one fundamental purpose, and that is to minimize energy gradients. So, for example, why is this little circuit right here able to show, like in a minute, to find a beautiful little centroid, resonant centroid, because it's the minimum energy surface. The thing that's great is that when you expand that over an entire body, how are you sitting inside your chair right now? You're sitting there basically finding like because it's the easiest center of balance, right? When you've got a nervous network that is a complete neural system plus motors that is optimizing the energy efficiency for the entire network, regardless of the state that it's in, you're now in something that gets damn close to feeling, looking, and behaving like a real living thing. Not that I'm saying biologists will eat the crap out of me, but you know, $200 million a year.
So the coupling of a neural net with
a nervous net,
is that embodied in these machines?
Yes, it is in all cases. And the thing was, is that
how many neurons are in the neural net?
Oh no, the thing. Well, I'm sorry. In these devices, no, none of these things actually use any neural nets. But in my original, in the prototypes that I'm building right now, right? I mean, that's the thing that basically shows the greatest range of surprising results. That is a device which essentially sort of, you know, tries this, tries that, tries this, tries that. Fuck it, I'm going. Right? And when you sort of realize, basically, geez, that's interesting, you know? Because there's nothing better than a robot that does something semi-intelligent, something that you could recognize as semi-intelligent without you having to program it, right? Because then you suddenly realize two things. Number one, A, how can I repeat it? And B, how can I get credit for it? Okay, and so this is what's going to be very important, is suddenly realize nervous networks is the cheapest way to basically get the most surprising results from robotics. But in terms of getting sort of like general results, that is, seeing the necessary components of neural nets. You know, like, why do you need, you know, like an appropriate hidden layer, 3-layer neural net to basically sort of, you know, optimize walking structures inside mechanisms? You can see it. When you see a robot sort of, you know, get its foot stuck, and then a second later it gets that foot out of the hole again within seconds. Was it the proper mechanics? Was it luck? Was it the neural network basically remembering? Well, it's not until you actually start looking at the data that you sort of realize I need much better statistical analysis software. And so the fact is that it is repeatable. And
how big are the neural nets you're dealing with?
Typically I deal with things on the order of 16 to 30 neurons, based upon 4 or 5 layers.
Recurrent or feed forward?
Yes.
Both? Yeah.
Well, the thing that's great about these things is that because the things are modular, right? Yeah. The great thing about these little circuits right here is that they're trimodal, so you can actually turn them off electrically. Yeah. So the neat thing is you can build structures and then just basically say, okay, well, let's play the brain game, okay? It's a living robot, and basically let's start turning off. Oh, I'm going to turn off you, and turn off you, and turn off you, and turn off you. Right? And you get that. One of the funnest things I like about a lot of my analog stuff is you get something which is working like this, 3 or 4 of these things walking, and then you take a toothbrush, cover it with water, and while it's walking you go across the analog. And what you'll see is something amazing. The robot will go from, you know, like a coherent behavior to all of a sudden, and then you'll suddenly realize it's slowly coming back as the water evaporates. But it doesn't come back in a slow method, it comes back in a punctuated way. That is that it finds the new radial basins, based upon like how fast things are working, and then all of a sudden it forces its way, and all of a sudden to the point where basically now it's like drags its foot like Quasimodo, where water evaporates, and then it starts walking like this. But the thing was is that there was this mad time, where obviously there was complete discoherence inside the circuitry. But the thing was is that you can't do that. Well, you can do that with your software if you've got very sophisticated software. But this is 15 cents each, and a toothbrush is only like 25 cents. So, I mean, that's an interesting way to find, you know, like the necessary variations on behavior. And this looks really cool, because I do that technique with my nervous network structures, just so I can find out what sort of things my robots are actually capable of. Because that's when I find out that there's a brand new walking gait that I'd never discovered before. Because I could not go through every possible permutation, so like, you know, a 16 neuron nervous net with a neural net hybrid. But the fact is a little bit of evaporating water allows me to make discoveries that have gone on to basically help me make robots. The thing is that in terms of, you know, like performance to silicon, but fun to silicon, right? I strongly recommend, you know, like look me up. I've got tons of it. Okay, I think I've pushed my time, but thank you very much indeed.